Dr. Kevin McCormack. He's no stranger to EGI. He was originally here and left back in 2009 to go to Stanford to get his training in geophysics. So he's back now as a postdoc, and so Kevin's going to talk to us now about seismicity. So, Kevin.
Awesome, thank you. You first. Hello, good afternoon. So my name is Kevin McCormack, and I'm going to talk today about induced seismicity in carbon sequestration. I'm a research scientist here at the Energy and Geoscience Institute, and let's get underway. So, oops, I don't know where to go. So just as an outline of the talk, I'm going to start with a brief introduction, talk about sort of the mechanics of induced seismicity, and then we'll talk about probabilistic hazard prediction at a site in New Mexico, in the San Juan Basin in New Mexico. And then we'll talk about fault curvature, how the curvature of a fault might impact seismic potential, or at least seismic hazard potential. And that'll again be at the site in the San Juan Basin in New Mexico. So moving on to our brief introduction. So as we know, if we inject a fluid into the subsurface, it pressurizes the formation you inject into. That pressurization has a poroelastic effect around the region of pressurization. And that if it impacts a fault that's present just in situ in the earth, that can host an earthquake, and it can host a large earthquake. I mean, it's possible. And so we really want to avoid that. Just as a community, we want to avoid having a large scale earthquake from carbon sequestration, from hydraulic fracturing, from EGS. We just don't want these big events. And so the majority of this talk is going to be focused on just trying to avoid hazard in these carbon sequestration projects. And so just as an anecdote, what we're really trying to avoid is losing the social license to operate. So in I think it was 2011, a magnitude 2.3, that's not a terribly large earthquake, but magnitude 2.3 caused the United Kingdom to put a 3-year moratorium on hydraulic fracturing, just because they lost the social license to operate. So just hounding the point a bit, but we don't want these events. So what is the mechanism by which these events occur? Well, if you increase that pore pressure and you cause these faults to pressurize, the fluid in the fault supports some of the normal stress because fluid can support normal stress. However, it doesn't support any of the shear stress resolved along the fault because fluids can't support shear stress. It's why S waves don't travel through fluids. And so what happens is we decrease the effective normal stress on the fault, and that causes the Coulomb failure function to increase. And so what that means in terms of a Mohr circle is we have an initial stress state here, and that change in pressurization causes the effective stress to change and bring the stress state closer to the failure envelope, which is how these earthquakes can occur. Now, there are many other mechanisms by which these earthquakes can happen. It's not just the pressurization of a fault. You can also have poroelastic effects, which, as I mentioned at the start, when you have that injection zone, that pressurized zone, the region around it gets perturbed by the fluid holding some of the stress. And so that can cause changes in the Mohr circle and the stress state. And then you can also have thermal mechanical effects, which is essentially where if you have a fluid that's at room temperature at the surface and you inject it deep into the subsurface, it's much cooler at the surface and the subsurface is much warmer. And so you have a kind of thermal shocking effect, and that can cause changes in the stress state as well. And then finally, you can have Coulomb stress transfer, which is where if a fault slips at one location, the region around the fault, the stresses in the region around the fault get perturbed such that you can change the stress state. And if the conditions are right, the orientations are right, you can actually bring faults to fail because a different fault failed. And so all of this is really well understood. This has been understood since 1890, I think, is when Otto Mohr first develops his Mohr circles. And what we're in the sort of the technique we're trying to do is we're trying to understand this Coulomb failure function, the CFF, which is the distance from the pole, which is the point in the Mohr circle that represents the fault, to the failure envelope. And this is a function of the shear stress, the effective normal stress, and the coefficient of friction, which if you just sort of look at it and think about geometry, makes perfect sense. And we want to look in this talk, what we're going to do is we're going to look at how how this well understood system, it's been well understood for more than 100 years, how this system can be understood, even we can have a better granularity of the understanding of the system. And what we'll look at specifically in this talk is probabilistic Moore circles, where we actually take input parameter distributions and vary them in a Monte Carlo sense and create a probability, a distribution of the Coulomb failure function. And then in the second part of the talk, we'll look at how the curvature of a fault. So instead of having a single pole that represents a fault plane, we won't use a plane, we'll use a distribution of the fault planes, the orientations of the fault planes, and that will lead us to a more spatial understanding of hazard along the fault. So without further ado, let's get into probabilistic hazard prediction. So this stems from the San Juan Basin Carbon Safe project. You've heard about it a little bit. It's led by William Apamo at New Mexico Tech. And it's a commercial feasibility test of carbon sequestration. It's in the San Juan Basin in northwestern New Mexico. It's intending to store a lot of carbon dioxide. It's trying to be a big storage hub. And they're even applying for more funding as we speak for additional resources to do even more with the project. And so it's currently applying as well for a class 6 permit, as we were talking about before. And this is to have the license to actually inject the CO2 into the subsurface. And so the first thing that I like to do in these sorts of studies is look at what is the seismicity that's taken place in the past. So this red outline indicates the basin boundary. The hogback monocline in green indicates the structural formation that is of interest to us in this study, as you'll see in a second. In this green region in light green is the area of interest for the project. Now, these green triangles represent the seismic stations, the stations that record the data. And these little dots are the seismic events. They're color-coded by their magnitudes. And the thing I'll point out two things really quickly. One is that the majority of the seismicity concentrates along the periphery of the basin, and that's mostly due to the structural complexity of the periphery of the basin. In the center of the basin, it's sort of competent flat-lying strata where you just don't have as many faults present, so you don't host as many earthquakes. So the other thing I'll point out is that in the region of interest, especially along the hogback monocline, we have very few events that were recorded by our network. So the first thing, or I guess suppose the second thing you do is you want to look at the state of stress. You want to say, okay, so what are the stresses acting in this basin? And so we use the extended Eaton's method, which is not the greatest method for understanding stresses, but it gives us a start. And what we see in this plot here of depth versus stress is that the two horizontal principal stresses are very close together. It's a radial normal faulting environment, and that'll be important in a moment. The other thing we need to do as we sort of get our input data is we need to look at what faults are we aware of, what faults are present in the basin that might host these large events that we want to avoid. And so when we look at these faults, we found 5 faulting scenarios. These are 5 possible scenarios that may be of interest. However, there's this one, the hogback flexural faulting area in the top there, that is of more interest because of what I'll show later. And I wanted to describe what this is. This is a series of faults that have been folded as the monocline took place, and yet the competent strata that folded and slipped past each other in flexural faults, which created discontinuities in the surface or in the subsurface, and which represent the boundaries between the strata. And these and so you have a series of subparallel faults representing these hogback flexural faulting area. Now, when we do our probabilistic Moore circles, we take distributions of the input data. We do a Monte Carlo approach, 20,000 realizations for each scenario, and we get a distribution of the Coulomb failure function for each of the 5 scenarios we are aware of. And so there's this one, the hogback flexural faulting scenario, that's higher than the rest. It has a higher hazard than the rest. It's closer to failure than the rest. And so we need to inspect that a little more carefully. And so, as I was saying, these are these strata that have been folded and slipped past each other. And we are also aware of about 20 million barrels of wastewater that's been injected into the same formation that's been proposed for the carbon sequestration. And this is sort of a pressurization test that's taken place. And because of this, or at least while this is taking place, we've also not seen much seismicity. That figure I showed at the start really didn't show much seismicity. And so we think what's going on with this area is that instead of having a big, large fault that can host a large earthquake, you have all these subparallel faults from the flexing of the basin. And as a result of that, you have microseismic events, and the seismic slippage gets distributed along all those subparallel faults. So the last thing we can do with an analysis like this is look at the sensitivity of each of the input parameters. So on the x-axis, you see the Coulomb failure function. On the y-axis, you see the different input parameters that we put into the model. And so the dip is always a strong sensitivity, and the strike in the least principal or in the SH max orientation are always low sensitivity, and that's because of what we know about the stress state and the orientation of the fault. The dip is a very uncertain parameter, so we used a very large distribution for the dip, and so we couldn't. And so as a result of that, we have a very large sensitivity on the dip. It's just 1-to-1. And then for the SH max orientation in the strike, we know it's radial normal faulting, and so because of that, the strike of the fault is not very relevant to its stability in the stress field. And so because of that, these two parameters really aren't very relevant in the study. And also note is that this principal stresses are intermediate in most of these figures. So in summary of this section of the talk, the input stresses and orientation are required to run this analysis. The injection appears to be safe for most of the region of interest, but the flexural faults did have a high Coulomb failure function. And then by looking at the saltwater disposal in the geologic framework, we can realize that the hazard really may not be very significant. So thank you. And let's move on to the fault curvature section of the. Oh no. So the fault curvature section of the talk, we can observe that in many previous studies they use a planar approximation of a fault. So they just say the fault is planar, but we're aware that in geological situations there's roughness defaults, there's rugosity defaults, and there's curvature defaults. All of these are not planar features. And so we took a realization of those hogback flexural faults that I was just talking about, this point cloud that curves with depth because we know that the basin is curving like that. And so we discretize these faults into these close packed hexagonal spheres where any data that came into a sphere was analyzed together. And so what it does is it discretizes the analysis of the fault based on where you are on the fault. And so we have a discretized version of the fault. And we did Bayes' law. So this is a Bayes diagram. We started with the data for where the orientation of the fault is. We go up through a regression to get a dip and a strike, a distribution of the dip and the strike, which we feed into a geomechanical model. And we put the input parameters that we used as distributions for the first part of the talk into the geomechanical model and created a Coulomb failure function, which is a distribution of the Coulomb failure functions for each of the discretized points. And we also did this with Krieg models. So we did this for all of the points in used together for the Krieg model, and we did it for each of the individual spheres for the discretized model. So what this looks like is you have these spheres where these are the discretized models with different levels of discretization. And you can see that we've actually highlighted a region in the fault that has a higher hazard than the rest of the regions. And so if we look at the Krieg model, we have the Coulomb failure function, which is a function of location along the fault. And so that's the hazard changes depending on where you are on the fault. And so in summary of this part of the talk, when we have information about the curvature of the fault, this could be a useful technique. It's not just the orientation of the fault that changes the curvature of the fault, but also the state of stress can change from one portion from one depth to another. And so that's a factor that comes into this as well. And then this is not applicable for all situations. You may actually be better off using a planar fault for many situations. And so in summary of the overall talk, we have the probabilistic hazard prediction section, which indicated what the hazard, or at least a distribution of what the hazard is on different locations, different fault scenarios. And then also we had the fault curvature section, which gave us a spatial understanding on the hazard of the fault. I'm sorry I went over. Yeah. There is a difference. There's definitely a difference, and what I think it has to do with so you realize that like the planar is just like one realization, and then the discretized version you have a ton of realizations, and the difference is like especially in the discretized, the spherical discretization, that I think there are edge effects to that, and so I think the overall hazard becomes lessened, but generally they're about the same, as if I remember right. Yeah, yeah. Uh-huh. Well, so we had data from the amount of pressurization we expected from the carbon sequestration, but then there was also we had to use an input parameter for what we expected the pore pressure to be in situ, and I honestly can't remember. I think we must have taken that into account, but I'm not sure. Oh. Yeah, so we did. In that case we did, yeah.
We gave him all the data.
All right, thank you.
Well, Kevin, 22, very complex.
That's my phone.
Thank you so much.
Now we're going to squish two speakers into a 20-minute talk here.